The definition extends to the general case of n sets where n is greater than or equal to 2. An element of capital S sub 1 times capital S sub 2 times ellipsis to capital S sub n is an ordered n tuple, x sub 1, x sub 2 through x sub n, where for each I equals 1 through n, x sub I is an element of capital S sub I. The definition of game frame is as follows. Definition 2.1.1, a game frame in strategic form is a list of 4 items, a quadruple. Open bracket capital I, open parentheses capital S sub 1, capital S sub 2, ellipsis, capital S sub n, close parentheses, capital O, F, close square brackets, where bullet point 1, capital I equals set 1, 2 through n is a set of players lowercase n or n greater than or equal to 2. Bullet point 2, open parentheses capital S sub 1, capital S sub 2, ellipsis capital S sub n close parentheses is a list of sets, 1 for each player. For every player I is an element of capital I. Capital S sub I is the set of strategies or possible choices of player I. We denote by capital S the Cartesian product of these sets. Capital S equals S sub 1 times S sub 2 times ellipsis times S sub n. Thus an element of capital S is a list. S equals open parentheses S sub 1, S sub 2 through S sub n close parentheses, consisting of one strategy for each player. We call capital S the set of strategy profiles. The third bullet point, capital O, is a set of outcomes. The fourth bullet point, F colon capital S yields capital O is a function that associates every strategy profile S and outcome. F of S is the element of capital O. Using the notation of definition 2.1.1, the situation illustrated in figure 2.1 is the following game frame in strategic form. First bullet point, capital I equals the set 1, 2, letting Sarah be player 1 and Stephen player 2. Second bullet point, open parentheses, capital S sub 1, S sub 2, close parentheses, open parentheses, the set is split still, split still, thus capital S sub 1 equals capital S sub 2 equals the set of split still, so that the set of strategy profiles is capital S equals the sets split split, split still, still split, still still. Third bullet point, capital O is the set of outcomes listed in table 2.1. Fourth bullet point, F is the following function. S colon split split, split still, still split, still still. F of S colon 01, 02, 03, 04. That is F of split split equals 01 or outcome 1. and F of split still equals O2 or outcome 2, etc. From a game frame, one obtains a game by adding for each player her preferences over or ranking of the possible outcomes. We use the notation shown in table 2.2. For example, if capital M denotes Mexican food and J denotes Japanese food, then capital M is better than J for Alice. It means that Alice prefers Mexican food to Japanese food, and M is just as good as J for Bob. It means that Bob is indifferent between the two. Capital O, squiggly or greater than, sub I. Restart. Notation. O, squiggly, greater than or equal to, sub I. O prime. Player I considers outcome O to be at least as good as O prime. That is, either better than or just as good as. O squiggly greater than sub I O prime. Player I considers outcome O to be better than outcome O prime. That is, she prefers O to O prime. Notation O squiggly line is just as good as O prime for player I. Interpretation, player I considers outcome O to be just as good as O prime. That is, she is indifferent between O and O prime. Table 2.2, notation for preference relations. Orange R circle. The at least as good relation, squiggly greater than or equal to, is sufficient to capture also strict preference, squiggly greater than, and indifferent, squiggly line. In fact, starting from squiggly greater than equal to, one can define strict preference as follows. O prime is better, O is better than O prime if and only if O is better than or just as good as O prime, and O prime is not better than or equal to O, and one can define indifferent as follows. O is just as good as O prime if and only if O is greater than or is just as good as or better than O prime, and O prime is just as good as or better than O. We will assume throughout this book that the at least as good as relation, squiggly greater than or equal to, for player I, of player I, which embodies her preferences over or ranking of the outcomes, is complete. For every two outcomes, O1 and O2, either O1 is better than or equal to or better than or just as good as O2 for player I, or O2 is just as good as or better than or just as good as O1 for player I, or both. If transitive, if O1 is better than or just as good as O2 for player I, then O2 is better than or just as good as O3 for player I. Then O1 is better than or just as good as player 3 for player I. There are at least 4 ways of representing or expressing a complete and transitive preference relation over or ranking of a set of outcomes. For example, suppose that capital O, the set of O1, O2, O3, O4, O5, and that we want to represent the following ranking expressing the preferences of a given individual. O3 is better than O5, which is just as good as O1. O1 is better than O4, which in turn is better than O2. Thus, O3 is the best outcome, and O2 is the worst outcome. We can represent this ranking in one of the following ways. As a subset of capital O times capital O, the interpretation of O and O prime are elements of capital O times capital O. That is, O is at least as good as O prime. The set of O1, O1, the sets of O1, O1, and O1, O2, and O1, O4, and O1, O5, and O2, O2, and O3, O1, and O3, O2, and O3, O3, and O3, O4, and O3, O5, and O4, O2, and O4, O4, and O5, O1, and O5, O2, and O5, O4, and O5, O5. By using the notation of table 2.2, O3 is better than O5, which is just as good as O1, which is better than O4, and that's better than O2. By listing the outcomes in a column, starting with the best at the top and proceeding down to the worst, thus using the convention that if outcome O is listed above outcome O prime, then O is preferred to O prime, while if O and O prime are written next to each other on the same row, then they are considered to be just as good. Best O3, then O1, O5, and O4, worst O2. By assigning a number to each outcome with the convention that if the number assigned to O is greater than the number assigned to O prime, then O is preferred to O prime, and thus if two outcomes are assigned the same number, then they are considered to be just as good as For example, if we could choose the following numbers, O1 yields 6, O2 yields 1, O3 yields 8, O4 yields 2, O5 yields 6. Such an assignment of numbers is called a utility function. A useful way of thinking of utility is as an index of satisfaction. The higher the index, the better the outcome. However, this suggestion is just to aid memory and should be taken with a grain of salt because a utility function does not measure anything, and furthermore, as explained below, the actual numbers used as utility indices are completely arbitrary. Definition 2.1.2. Given a complete and transitive ranking of better than or just as good as of a finite set of outcomes, capital O, a function, capital U, colon, capital O, yields outline capital R, where outline capital R denotes a set of real numbers, is said to be an ordinal utility function that represents the ranking better than or just as good as if for every two outcomes O and O prime, capital U of O is greater than a capital U of O prime. If and only if capital O is better than O prime. And capital U of capital O, the utility of O is equal to utility of O prime if and only if O is just as good as O prime. The number utility of O is called the utility of outcome O, or capital U, open parentheses, O, close parentheses. The notation f colon x yields capital Y is used to denote a function which associates with every x is an element of capital X. An element y equals f of x with y being an element of capital Y. Superscript B. Previous was superscript A. Thus, O is better than or just as good as O prime if and only if the utility of O is greater than or equal to utility of O prime. Capital orange R. Note that the statement for Alice, the utility of Mexican food is 10, is in itself a meaningless statement. On the other hand, what would be a meaningful statement is for Alice, the utility of Mexican food is 10 and the utility of Japanese food is 5, because such a statement conveys the information that she prefers Mexican food to Japanese food. However, the two numbers 10 and 5 have no other meaning besides the fact that 10 is greater than 5. For example, we cannot infer from these numbers that she considers Mexican food twice as good as Japanese food. The reason for this is that we could have expressed the same fact, namely that she prefers Mexican food to Japanese food by assigning utility 100 to Mexican food and 25 to Japanese food, or with any other two numbers as long as the number assigned to Mexican food is larger than the number assigned to Japanese food. Superscript 4. Note that assigning a utility of 1 to an outcome O does not mean that O is the first choice. Indeed, in this example, a utility of 1 is assigned to the worst outcome, O2, the worst outcome because it has the lowest utility, which happens to be 1 in this example. It follows from the above remark that there is an infinite number of utility functions that represent the same ranking. For instance, the following are equivalent ways of representing the ranking. O3 is better than O2, which is better than O3 is better than O1, which is better than O2, which is just as good as O4. Open parentheses, F, comma, G, and H are 3 out of the many possible utility functions. Colon. We have an outcome yielding O1, O2, O3, and O4. And we have a utility function 3, F, G, and H yielding the outcomes. So the utility function for F of O1 is 5, and F of O2 is 2, and F of O3 is 10, and F of O4 is 2. For utility function G, G of O1 is 0.8, G of O2 is 0.7, G of O3 is 1, G of O4 is 0.7. For utility function H, H of O1 is 27, H of O2 is 1, H of O3 is 100, H of O4 is 1. Utility functions are a particularly convenient way of representing preferences. In fact, by using utility functions, one can give a more condensed representation of game